Hello, everyone, and welcome to this new Shifting Gears with SDV webinar. My name is Amandine, and joining us today is Manuel Fessler, who will be presenting on the topic of application framework, the fast lane to distributed automotive applications. If you have any question for Manuel as we move through today's presentation, feel free to ask in the chat or use the Ask a Question tab. Without any further delay, Manuel, over to you.
Perfect. Thank you very much for the nice introduction. Let me just share my screen. Okay. So you can see my slides, right?
Yes, we can see your slides. Thank you.
Perfect. Then let's dive directly into the topic, application framework. So what's on the agenda for our webinar today? This project, the application framework, is part of Eclipse SDV incubating project, the Eclipse Automotive API framework. So beginning, I want to give you some context. What is the project all about? Who is involved? And kind of set the context for this webinar. Then let's look a bit into the technical details. What's the concept behind the application framework? What's the idea? And I also want to share some really technical insights with you in form of a live demonstration. And here we will do a sample demo on a communication use case, illustrating the capabilities of the application framework state of today. And then hopefully this is a trigger for you to experiment with the project. So you find everything in our GitHub repository. I will also share it later. And hopefully it's of interest and a starter for you. And finally, some conclusions. We have some topics in the pipeline, and I would like to give you some takeaways from today's webinar. Good. So the Eclipse Automotive API framework. Originally, it's a project, or it's based on a project done between ZF Group and Vector Informatik. ZF, most likely known to you out there, here in this project in the role of an automotive supplier, contributing to HPC, so microprocessor-based ECU projects. And the idea is here to have software developed at ZF in-house to provide this to OEM projects in an off-the-shelf manner. And Vector, the company I'm with, is in this project acting as a provider of an AUTOSAR adaptive middleware, partnering with suppliers and OEMs, because the middleware is finally glue between application and the platform owned by the OEMs. Now, let me illustrate roughly the scenario. So what do we see? We have in the supplier side, a lot of developers, engineers working on application codes, logics, control loops, ADAS systems, and more. And here, not for all the projects, but a prominent pattern here is to develop model-driven. So doing some modeling steps first, for example, in UML or other ecosystems. Also, Simulink is an important tool in this area. And working with such ecosystems means typically a graphical user interface. Modeling can be done here, development and also testing in model in the loop testing, for example. And we have a closed feedback loop. So working with this graphical user interface covers all the needs of the developer, from front-loading, upfront modeling, the development, sometimes also based on graphical systems, and finally the testing. In the end, to bring those application artifacts into some target system, an ECU project, we see code generation, export steps to a target programming language, be it C, C++, in the future maybe also Rust. Now, switching sides from the supplier, the application got developed here, exported, and now is ready to be integrated at the OEM side into some ECU project, so part of a vehicle. And what we see in the OEM side is often a team or teams working on an overall system architecture. And from there derived, we have specifications of the different ECUs in the vehicle. And in case of the HPC system, we have typically an operating system, POSIX-based typically, and on top a so-called middleware, automotive grade, fulfilling certain quality requirements. And now one prominent solution here is AUTOSAR adaptive. And here the pattern, the work mode is specification first. That means we have a clear definition of what the ECU is supposed to do, how its outer surface looks like, what data is going in and out. And often code generation is then used to create and customize the middleware accordingly. And now we have the situation, we have application artifacts resulting from model-driven tools and ecosystems exported to a target programming language like C++. And we have on the other hand side, from the bottom side, the platform, operating system, and middleware based on some concrete specification. And now in the end, we have a final integration step taking place at the OEM side. And this is where two worlds collide, where often late in projects we see problematic and laborious steps to come up with the final deployable unit. So that's the scenario described. And this brings me to the mission statement for this project. So the plan, ZF and Vector discussed and said, okay, seems like here is a missing link between middleware parts, application parts, and the integration. It's too cumbersome. We need something to break up this dependency between application development and integration. And the solution is the project we have here at hand. It's the intention to provide a framework, including APIs, tools, and workflow, to come up with a solution as illustrated here on the left-hand side. So suppliers provide application artifacts. The API used for the development and in place is covered by the framework. It's open source, so that's why I'm here today in Eclipse SDV. That means we have no vendor login, often feared by companies in the automotive sector to be logged in with a certain company, supplier, or solution. This is avoided here by making the framework open source from the beginning. And it allows to do different levels of testing. Also using the framework, application artifacts can be tested on the unit level using the framework, and pre-integration tests already can be done at a supplier side to best prepare the step towards the OEM target system. And now the integration step, also the OEM, according to this proposed solution, works with the framework and integrates the application artifacts then with some middleware XYZ. And the plan or the vision for this project is to create a triple win situation for suppliers to enable them supplying ECU projects with business logic and algorithms off the shelf. Then middleware and basic software providers responsible for middleware XYZ, and finally the vehicle manufacturers, where all those pieces get integrated finally. And this motivated us in sum to start this project. And in the meanwhile, we are live for roughly half a year now. And here some project facts, just in case you want to check out later the project website, mailing list of our project, the GitHub organization, and just in case you're interested in the license, it's Apache Software License 2.0 that we apply for this project. Then some more technical details of the application framework, the core component of this Eclipse project. So on the right-hand side, we see state-of-the-art, the situation today. Applications, no matter which flavor, need to be integrated with the middleware directly. And this is exactly the situation we want to break up and to provide a solution that allows lower layer independent design, implementation, and test of distributed applications. And this leads here to this thin but new layer to the microprocessor stack, the application framework, here marked in red. And this layer is a modeled and a generated layer, but this configuration aspect is reduced to a minimum, and we tried to make it as convenient as possible. And it's not only this layer, but it's a complete workflow and the corresponding tool that allows and to use and that allows to work with the framework. And the workflow covers everything from the very left-hand side, project initialization, project startup with templates, etc., down the road up to build and test of final deployable artifacts. Now, let's look more into the building blocks we have. So the solution of the application framework applies at compile time, and it puts the focus on the executables that later run on the POSIX-based system. The foundation of everything is a data model. It contains different packages. On the one hand side, we have agnostic packages, describing data types, for example, interfaces, etc. But we also do have middleware-related aspects in order to support different lower layer communication and middleware stacks. On top, and the user-facing part is configuration as code. So a basic principle we tried to apply here is to have everything as text. So configuration is done in text. The tooling is text-based, a command line tool, in order to be ready with this framework for good integration with CI/CD ecosystems, so automated pipelines, and also the current hype with KI-based system agents, etc., where it's also beneficial to have text-based solutions that can be used and integrated well with such KI systems. So this configuration as code in Python layer is an abstraction of the model and the user-facing part. Reality shows that there are only few projects that really start on a green field. We have a lot of legacy code and legacy projects in the automotive domain, and reuse is key in order to be accepted and in order to be adopted. And that's why we have this input stage, model import from different artifacts. One potential format is the VSS, Vehicle Signal Specification, as defined and maintained in Covisa. But here I explicitly wrote others. So here the project is completely open and can be extended with other formats. You can name them. So for example, Franca is one option. We also see in Covisa the IFAX project. So all potential input formats that serve as a starting point. In the end, we have imported artifacts. We have user added parts in configuration as code, and this consolidated database is then stored in a data exchange format. We chose the JSON format for that purpose, but you can think of it as a model database. So just to store the information. And the reason for that is to have a common data source for the generators, which are also part of the framework that we use. One hand side for the generation of API, COM and persistency, for example, are currently supported here. We generate implementation and test stubs. Also, the build environment files currently based on CMake are based resulting from generation. So there are artifacts each project needs, but nobody wants to write and maintain are provided by the framework to simplify and ease the life of a developer as good as possible. Also, we have static code artifacts covering everything you could think of executable level housekeeping code or boilerplate. So runtime aspects, instantiation of classes, logging, error handling, and state management. And together, those two pillars find its way into the final executable. That's why I wrote here the focus is put on the executable. So maybe one step back, we see that's state of the art developing for HPC. You have the middleware interface and below some transport IPC based in most cases. And what the app framework introduces here is on the one hand side, abstraction modules, so kind of wrappers for different middleware layers, be it AutoSAR based, be it DDS based, or whatever you can think of. And we have the control module basically covering this static code for the runtime aspects, etc. So all the, as I named already, executable level housekeeping code. And on top, we have a shared domain between the framework and the developer. This is where the application framework generates implementation and test stubs and provides means to modularize the application. So the term we use here is application modules. This is standalone application logic that can be, that can stand for itself and be developed in a separate unit. This enables reuse, but also is good in terms of testing, because the first level of testing is typically unit testing, and you can think of a first test stage also supported by the framework. We have support for Google Test included to create a unit test for each application module developed with the framework. And with that said, I can now also give a clear definition of what an application actually means here in this context, because it's a widely used term and often a clear definition is missing. And the meaning we have here in this project for application is nothing but a thematic bracket. So it can be, for example, an ADAS application, a lane keeping application, or something similar. So putting stuff together that belongs together. And on technical level, an application can consist of multiple executables, and each executable again can consist of multiple application modules. And with that, I would like to directly move on and give you a live demonstration to show you the framework in practice and some more details and technical insights to get an understanding and a feeling for what the framework actually is about. And the live demonstration is split into 3 parts. We have design stage, typically done by people named architects, or we also see a lot of definition taking place in the open source community, for example, in the already named VSS project, where signals often used and present in vehicles are defined. So in the first stage, we will look into how data types, interfaces, and executables can be defined and designed. Those model artifacts then serve as input for the implementation stage. design of application modules, development of the business logic, and unit testing. This is the scope of the developers. And finally, we have the integration stage where we have instantiation steps to do. So we need to instantiate the application modules, the platform side, and to wire them among each other. So basically integration of application with the platform, with the middleware, etc. And this also allows us to do system level tests of our created deployable artifacts. So in the demo, I have illustrated it here. It's a straightforward flow, but it's important to state that this is not reality. So there will, in reality, be a lot of feedback loops. I don't know, developers are missing some data. They have a feedback for the architects, etc. And also this feedback loops and iterations for sure are supported and possible. Even the framework encourages to do this. And developers, for example, have the possibility to extend the design parts to be not blocked by missing input artifacts, for example. So already named VSS. So also in the demo, we will use the VSS catalog as available from the open source project in Covisa as an input artifact. So it defines in a tree structure different signals typically found in a car, in a vehicle, like the chassis, the cabin, I don't know. We will see some examples later. And the already named teams or people that typically need to collaborate in such projects, and where we want, on the one hand side, to enable good collaboration between them, but we also want to unblock the individual teams with the framework such that, there are no interdependencies, no friction between the different teams, and co-work and coexistence of those teams and project work can become possible. Good. Then let's dive into the live demo. I will shortly switch to my VS Code window. But before we do that, we will now see for those 3 stages I have just presented 3 different project types. So we have in the app framework 3 different project types, and the first one is the interface project I would like to introduce first. And here we will now see how input artifacts can be imported, how the config as code front end can be used by end users to extend. And in the example I want to share today, we will use the parking brake, the velocity information as defined, and the ambient light as defined in VSS, and the data exchange interface is one that we will add in config as code on your own. And here on the right-hand side, I will now, in the following slides, step by step, build up the complete workflow consisting of those 3 project types. And we see here the interface project is an optional project because all those steps can also be directly done in the application module project, which is about to follow. But in any case, the interface project is a nice tool to give bigger projects a structure. Okay, now let me switch here. Before we start, so just in case this webinar sounds interesting to you and you want to experiment with the framework yourself, you want to do your own little example, I can just recommend you to check our Eclipse organization. And here in the application framework repository, you find all the instructions that you need. So we have included a container recipe, a Docker file is defined here, and also, let's switch back here, a script to build this container in place. And here in the getting started, you find the instructions for the two potential users. So we have a project contributor section if you want to make additions and contributions to the project. And we have the application framework user. This would be the instructions to follow in case you want to do a sample project and to play around with it. So first step would be to build the container and create a workspace. That's the only two steps I have already prepared up front, because I think we can save a little time and we don't need to look the terminal building the container. So this is something I prepared already, but now we start from scratch. One artifact I copied from outside. This is the VSS catalog. You find here the JSON export as you get it from the Covisa open source project. So this is the only artifact from outside. And now let's get started with the application framework. As I said, the tool abbreviation is VAF, Vehicle Application Framework, and it's a command line tool, and the commands divide into 4 categories. We have make-related commands, model-related commands, and project-related commands. The workspace is only one that you need in first place to create such a folder. So I have already executed this one. Here we get the dev container file for integration with VS Code, some VS Code support files, for example, a task JSON file that defines all the command line instructions and enables to use plugins like Task Runner to execute the command line commands without memorizing them. So, and with that, let's get started. First step, so I will switch a bit between command line and also the Task Runner plugin. So first command would be WAF project init. And we see here we have 3 different project types: an interface, an integration, and an app module project. And now we start with the interface project. I get prompted. Second. Yeah. Let's just use a random name, interfaces. And now we see in the workspace, a new project or folder is created based on a template. And in here, we find different files. We have this Python file, interfaces.py. So it's always the same name as the project that is used for the config as code template file. And now 2 steps here to do. First, we want to import the existing BSS catalog artifact. So now I'm just using this task runner. We see here always the command is WAF model import VSS. And just referencing the JSON file here. And now a new pair of files got added to my project. It's a Python file and a JSON file. And if you now remember the previous slide I have showed with the building blocks, this JSON representation is nothing but the base, the data model representing now in the app framework representation information as extracted from the input VSS catalog. And with the vss.py file, we have an importer file to the config as code level. So we see here, it just imports the derived model.json. And now we can import either single artifacts from the VSS import or with the star symbol, just the complete catalog. And now on top, so here you see some sample code. We can either uncomment it and change it, or let's add just a new interface. The entry point is always WAF pi for the config as code abstraction. And I want now to add to the already existing information from the VSS catalog my own data exchange interface, and now guided by IntelliSense and the IDE. I can define this interface as I need it. There are two basic communication patterns we have. We see it here. On the one hand side, it's the so-called data elements. They mimic a publish-subscribe pattern, so exchange of data elements. And the corresponding interface I will show later. The API is getters and setters, event handlers, etc. And on the other hand side, the second supported communication principle is the operations. They stand for remote procedure calls. So like operations, as the name implies, for remote execution. And now the interface can be seen as a bracket. So we can now add a data element to this interface. For example, here, my value. Let's use something simple, base type, UN16. And to define an operation, same pattern applies. Just give a name. And here we have in, out, and in-out parameters. Again, so it's all plain Python syntax. Let's use for example, a bool for this one. And that's already it. So for this simple example, we have now imported the artifacts from VSS. We have added our own interface definition with one data element and one operation. And the next step is to create the consolidated model artifact. And for that, we have this model generate step here. So you see here, WAF model generate. And this step just produces, again, a pair of files. We have the data exchange format, the interfaces, and the corresponding importer file for later use in app module and integration project config as code. And if we have a short look here, we see that we now here have stuff from the VSS catalog. Sorry. But we also see, in addition to it, the data exchange interface with the data element and the operation as we just added it using config as code. Good. With that, let me switch back. So this step completed, we can now move on to the second project type, the application module project. And in this simple example here, I would like to define and implement two of them. App module 1, consuming the parking brake information and the velocity from outside, providing the data exchange interface to the second app module. And here, just some random example, I want to control the ambient light and decide or activate or deactivate the ambient light in the driver's position if the car, so independence of the status of the car. If the car is in standstill, parking, the ambient light should be off. And if the car starts to move and is driving, the ambient light should be activated. So just a random example, but I think it illustrates the possibilities here. And in the app module project now, we have the same pattern. We can import either from interface projects or from the possibilities like VSS or other stuff directly, then config as code is needed here to define the interface flavors, consumer or provider. Also to define cyclic execution tasks, etc. And finally, again, we have code generation step, implementation steps, and test stubs that we can fill with our own content. Let's switch back now. There is a separate project type here, the app module project. So let's create a new one, app module 1, namespace just demo. And we see here again a new folder was created, and here in this project template we have some more content included. So package management dependencies are handled by Conan. That's why we have those Conan files here. Then the implementation folder, subfolder, is the space where the user and the developer later will find the application module stubs for implementation and testing. The model part is config as code, similar to what we see in have seen in the interface project, and we have two folders, the gen folders, source gen and test gen. The build environment is based on CMake. That's why we have those CMake list files pre-generated. And now shortly, let's switch back. So app module 1, 2 consumed interfaces and 1 provided interface. Now let's get started here. First step is to import now from our interface project. And here we just need to reference from our project the exported JSON file. And now we see here it got imported by copy. And here in the model folder, imported models, we just see a copy of the interfaces JSON and corresponding Python file. With that, we can, again, here, either in a selective way or with these star asterisk import the content from here. And now already prepared by the template, the app module 1, namespace demo, as given as command line parameters. And now we see here one example on how consumed and provided interfaces can be configured. Again, IntelliSense is supporting here. No need to memorize all the stuff. And the first consumed interface is the parking brake consumer for this example. And the interface now is one that we take from the interfaces imported catalog. And now we see here VSS, the root node, vehicle, and then the parking brake is part of chassis, parking brake interface. Top, and let's repeat the steps for velocity consumer interface. Velocity chassis, that's part of. So now there are different rows and wheels. So let's just take the front left wheel to collect some speed information. And the final one is then a provided interface for data exchange. And here, again, root node interfaces, demo, data exchange interface. And that's it. Here in the bottom of the file, we see a sample for periodic tasks that can be added. Maybe let's increase the period a bit. And here multiple of those app module tasks can be added also to the configuration. And now the project can be generated. And we see now here different artifacts get produced. Again, we have the already seen pattern of model, Python and JSON file. Good news here is, so in contrast to the imported model from the interface project, where we have the complete VSS catalog in place and the individually added data exchange information, we have 17,000 plus X lines of JSON. If we now look into the model JSON tailored to this app module, where we only use portions of the VSS catalog and the interface file, we see that the whole information reduces to only 158 lines. And this is the complete description of model information that is needed for this particular project, and shows that we do not propagate all the information to the next level, but a cleanup and tailoring is taking place. Next step here now is to check the implementation folder with its content. So we have different files created. We have the source folder. This is an implementation stub. We see here in the top some comments that illustrate the actual API, and maybe for data elements in operations, maybe we can shortly check how this actually looks like. So we have a consumer and a provider side. Let's start with the consumer, and we see here for our data exchange interface with the my value data element and the my operation remote procedure call, we get the following user-facing API to interact with those two artifacts. We have getters. There are two flavors. We have here the get my value, which reduces, returns a copy, and we have here the possibility to also get access by a pointer, so access by value and by reference. You can also use this register function to work in an event-driven mode, registration of a handler. And here in the bottom, we see the signature of an operation returning a future and the modeled input value and output value, which is defined in a separate header file, the bool out value. Exactly. And now to give this whole demo a little bit of meaning, let's introduce some sample code. So if, I don't know, let's just collect the velocity. So from velocity consumer, get speed, and if parking brake consumer is engaged and the velocity is greater 0, then I would like to send something out via the data exchange interface. So that's just some random code, and if the car is parking, I just send out 0. With that done, I can now build the whole project to check if the compiler is satisfied. And I find now here in my build folder some pre-built unit test file. And this brings me to the second part here in the implementation folder. Here in unit tests, we have prepared, based on Google Test, already the corresponding interface mocks. and a sample test which can be used as a template for other own tests. That means this application module 1 can be used in a standalone fashion and be supplied with data from the outside for parking brake and velocity. And on the other hand side, the output for the data exchange value can be checked. And this module 1 unit test then is available from here, and you see the typical Google test output. Yeah. Another nice feature is, so we have here some implementation stuff, and I presented it earlier. It's a shared domain between framework and the developer, the user. So just in case you are changing stuff, for example, here, changing the name or something, then this will be changed. And just in case there is something else that can't be directly modified, then we have integrated a merge feature based on Git merge that illustrates here in your CPP file the problematic areas, as you know probably from Git merge conflicts, and then you can easily resolve that. Yep. But that's the app module 1 complete. And now let's complete the app module parts. We need also the second application module. That's same steps again. So I will speed up here a bit to just complete that. So once again, we need to import the interfaces. From earlier. And module 2, we have consumed the data exchange consumer. And no, this one was demo data exchange. And we have one provided interface, the ambient light provider. This one is part of the cabin branch. I think it's light, ambient light, row 1. Driver side interface. Once again here, let's maybe increase a bit the period. Same steps apply here. So we can now generate the application module code, the interface codes in source gen, the test artifacts for the unit test into test gen, and the implementation steps here. And in this demo, let's just have some sample code also for this part. So data exchange consumer. So here we now consume the value. The value is 0. We have car is parking. Otherwise, car is driving. velocity is like that. And we can also now set via the ambient light provider, for example, set is light on false, and for the driving state, we set it to true. Just a random example. Let's build again for this part to check if the code is good so far. And with that, let's switch it back to the slides for a second. Now, the final project stage is the integration project. And here we integrate the two application modules as one instance for each module into one executable. And we build it together with the Silkit software in the loop middleware or platform side to a binary executable that we can execute and use for system level tests. And with that, so let's switch back here. Last project type, demo integration. Gives me again a project based on a template. It has basically the same structure as the app module project, and we start again with config as code. And here we now want to instantiate our application modules. So in first place, we need to import them from the previously completed app module projects. App module 1, app module 2. And we see now here we have those importer Python files included. And now we can start here. The template already prepares most of the steps. Let's create an executable, demo executable, for example. Then let's instantiate and add two application modules here in this part in the back. The control module settings as derived from the app module project can be overwritten, but that's a step I will just skip here. And now the wiring needs to be done. And here, in the first place, I'm doing this internal connection. So I'm connecting the app module 1 data exchange provider with the app module 2 data exchange consumer, just as illustrated here in the center of this drawing. And for the platform side, let's switch back for a second. We have those three, the parking brake, the velocity, and the ambient light still that need to be connected. And here there are the so-called connect functions. And we now use this connect to Silkit. And this is again app module 1. App module 1 consumed interfaces parking brake consumer and the velocity consumer. And for app module 2 provided interface app module 2 ambient light provider. And with that, the integration project config as code part is also complete already. And I can, similar to the app module project, generate the integration project now. maybe an interesting point to mention here. So below source, we have those application module projects now. And this little arrow indicates that this is just a symbolic link. That means importing the app module project to this scope of the integration project is nothing but a symbolic link, a reference to the original project, which lives standalone and can also be maintained in a separate repository. So this is just included for sure, also an integration by copy is possible here. This step complete. Now just leaves open to build the project. Hopefully I completed all the steps and did not miss out something. Otherwise, the compiler will just tell me. And while we are waiting here, let me shortly explain this detailed view. What did we kind of create in the integration project? So we have configured one executable, instantiated the two app modules, and we have connected them among each other. This is the data exchange interface connection. And we have connected them to the software in the loop test environment, test middleware, let's say, that's represented by the circuit registry, which can be seen as kind of a daemon or, as the name says, a registry, which our executable can connect with. The good news is no need to care about circuit related artifacts or in case of another middleware to take care of other middleware related aspects. This is encapsulated by the so-called platform modules. And with those platform modules, we introduce the wanted abstraction from app module and app development from the lower layer. And those platform modules can easily be replaced later on, for example, with corresponding modules for an AUTOSAR-based middleware or a DDS-based middleware. And the test executable visible here is one that I have already prepared up front. And now let's do the final step, install the whole stuff into the build, release, install folder. And you see here, we find already the circuit registry binary for execution of the software in the loop test. And we have the demo executable as configured right here. And to complete the demo, would now like to shortly execute the two of them. And hopefully we see then some output. So build, release. Okay, first place, I'm starting now the circuit registry just as a process to the background. And this is now waiting for awaiting connections. And the demo executable just goes here. Demo executable. We now see, okay, car is parking. The test executable is still missing. No input coming from the outside. And now let me just switch to the prepared test executable. I created this one just the same way as I did now for the demo executable. So same workflow, same patterns, and so on. All the same. Install opt test executable. Let's start this one. Now we see, okay, there are some actual values for velocity are changing. So it's stop and go kind of. And we see here car is switching between driving and parking mode. Exactly. And that's the demo complete. Let me now continue. We are almost at the end of this webinar with some conclusion. So I have two more topics I shortly want to pitch here. We have prepared also a VS Code extension, which does two things. So we have in the demo seen that I used this task runner plugin on the left bottom corner side, This is integrated in the VS Code extension in a bit more nicer way. You see here the different tasks from the command line tool illustrated and ready for use in VS Code. You don't need to memorize the command line commands. And the second nice feature for this VS Code extension is the visualization of integration projects. So, for example, here on our demo use case, you get rendered figures like this one, the demo executable with the app module 1 and 2, the different rows, arrows indicating the relation. And also from here, we have directly a link to the corresponding config as code and implementation files. This one is in the pipeline and soon to be published via Microsoft Extension Store for VS Code. And another topic which is in the pipeline is a so-called blueprint project. So we want to put the application framework and the whole automotive API framework project into relation with other open source projects. And this has two benefits. It will introduce new features to the framework and shows the relation between this Eclipse SDV project and others. And for that, the plan is to create the following blueprint project based on a scenario and VSS catalog from ZF. Plan is to extend the input formats by support for Covisa IFACs. Then showing the relation between Eclipse Automotive API Framework and Eclipse S-Core project by introducing a platform abstraction module for internal communication based on the S-Core communication module LOLA. And the external communication via Silkit is already available today in the project. So that's the whole blueprint idea complete, and the scenario, as you can see here, illustrates a speed hazard detection scenario. Two modules, and finally deployed in form of two executables. Good. Then let me conclude this webinar with the following takeaways. So I've presented the Eclipse Automotive API Framework and the app framework as a central building block or central part of it. It's a compile time solution for independent design, implementation, and test of distributed applications. It's best described by this thin layer, additional layer to the microprocessor stack, which comes with workflow and tooling, all text-based. So you have configuration as code, you're ready for CI/CD usage, and also the AI agentic workflows. And once again, because it's important for me to highlight what the application actually here means, it can consist of multiple executables and not only one, and each executable is modularized and allows the definition and integration of multiple app modules. And here I illustrated already the upcoming picture with a new platform module for the S-Core communication lower layer in place via IPC channel. So you see here, once again, a summary of the architecture of the app modules, the control modules, different potentially lower layers. And the good news here is communication on app module level on horizontal or vertical axis is, from the API perspective, identical for the developer. We have the control module relieving with all the stuff that can be automated or written once. We have the different lower layers. For example, in the demo, we have seen the Silkit. In the future, others, for example, the LOLA module will follow. Then, app modules as such have several benefits. The modularization allows reuse, it allows work split, and independent development from the lower layers also breaks up existing relations in projects and hopefully makes them more productive. Then we have seen that the whole thing is wired at compile time. And a prime use case for the app framework, as you already might have guessed, is that it can be used perfectly for the creation of so-called gateways. So several lower layers can be connected and integrated into one application or even one executable. You can have incoming data flows, outgoing flows via a different lower layer, etc. And this allows to create and cut this whole picture in the middle to realize kind of a stable contract for the app module developers. And last but not least, this demo has showed that fast prototyping is possible with the framework. You can create from scratch. So the only input artifact I used is the VSS snippet from the Covisa project. But other than that, everything was just created by the framework or by me in place. And we have seen that in roughly 30 minutes, a simple use case as the one with the ambient light is possible. And already today, pre-integration with the Silkit, another open source project, by the way, is possible and already allows to create and test mature application code. And with that, thanks for participating today. I hope it was a topic of your interest, and thanks again for having me today. And now I'm looking forward to get your questions. Thanks a lot.
Thank you, Manuel. I see that there is one question in the chat. Can you please share the link of the GitHub report? Thanks.
Yes, for sure, I can do that. Yeah.
Perfect. And while you're searching it, I would like to thank you again for that excellent presentation today, Manuel. And also, if there is anyone who has a final question, please feel free to ask it in the chat or use the Ask a Question tab. We are also looking to book more Shifting Gears with SDV webinar. If you're interested in presenting, feel free to fill out the form which I have linked in the chat. And finally, if you have any feedback on this program, we would love to hear from you. Just click on the green button that popped up and let us know how you enjoyed the talk. You gonna share it on the chat or you gonna share it
I shared
directly in the presentation?
Well, whatever you prefer.
Maybe you can also share it in the chat, and then we will see how to manage to send it to this person.
Okay, yeah.
So, though it doesn't like there is more questions, I would like to thank you, Manuel, again, and thanks to everyone for attending. I hope you all have a wonderful day. Thank you.
Thank you. See you next time. Bye-bye.